Okay, thanks very much, and thanks for the chance to give a talk here. I'm having a great time the few days that I'm here. So Ian said that I should give a background talk, so later on I'll give a talk about my own work. I didn't really know what the background of the audience would be, so I decided I'm going to try and be very elementary. If I'm being too elementary, or sort of start at the beginning of the story, if I'm doing that too much and I'm saying things that everybody knows, then please stop me. So I was going to just try and tell part of a story about how the cat-zero cube complexes and then the notion of special cube complexes have played a role in certain developments. So for the purposes of this talk, I think the end of the story will probably be Ian's proof of the virtual Haken conjecture. And the final ingredient of that was a theorem about groups acting on cube complexes. And I wanted to sort of tell you where these cube complexes arise and how the various properties of them might tell you certain things that you would like to know about groups acting on them. So Ian can leave now, certainly. Anyone else who wants to leave now is welcome to. And if you'd like me to tell you about something else, then stop me now and I'll do that instead. So anyway, the virtual Haken theorem says, so this is proved by Ian, says if M is a closed hyperbolic 3-manifold, some finite cover of M contains an incompressible surface, say sigma G, where G is a homogeneous surface. Okay, so this is the final part that was proved. There are many other parts to the story of manifolds being virtually Haken, but that was the final part that was proved. And so the 3 bullet point outline, maybe even fewer, goes as follows. So step 1 is find the 2 bullet point outline, right? Find an immersed incompressible surface with extra conditions. And this was done by Kahn and Markovich. So here incompressible just means pi1 injective, a map from a surface into the manifold that's pi1 injective in this context. And the extra conditions you can ask Jeremy and Vlad about. So that's not so this surface has to be embedded. So step 2 is lift this surface to an embedded surface in a finite cover. Okay, so those statements are entirely topological, and what I wanted to do today is explain how this gives rise to what's called a cat-zero cube complex, upon which the fundamental group of the manifold acts by combinatorial isometries, and how certain properties of certain kinds of cat-zero cube complexes and group actions on them tell you that certain problems like this, immersed things being able to be embedded in finite covers, can be solved using certain kinds of technology. So that's what I wanted to tell you about.
So in step 1, do you have to look for cover, or you can always find it directly in M?
Well, that's so the immersion. I mean, if it immersed in a finite cover, it would immerse in M. So yeah, but they do indeed work directly with M. Yeah, but it's really a problem about finding certain kinds of subgroups of the fundamental group. So you don't need to pass to any covers. They work directly. But I mean, it's obviously, it looks like a lot of progress towards this, but having an immersed surface is maybe very different than having an embedded surface. So this two-step strategy was a strategy that was known for, oh, I don't know, 30 years, probably more, as an outline of a strategy, but it's only over the last maybe decade that the tools came to do either of these steps. I'm not going to tell you anything about how to carry out step one. You should talk to Vlad and Jeremy for that. But I'm going to tell you sort of what it gives you from the point of view of these cube complexes. Okay, so that's the plan. We'll see how we go. So section 1 is cat 0 cube complexes. And this story really started with Sageev's construction. And what this does is it gives you a gadget that's the cat 0 cube complex that packages together the information about certain codimension 1 subsets of some object that you're thinking about. So the object you might have in mind here is the universal cover of your manifold M, and the codimension 1 things you might have in mind are the elevations of these incompressible immersed surfaces. If you take an immersed surface and you lift it, then the preimage of that has a bunch of surfaces intersecting each other in the universal cover that cut the universal cover up into something, some collection of pieces. If it were embedded, then in the universal cover you would just get a collection of topological planes cutting up H3, and you could take the dual action on a tree to start telling you something. But so what Sageev's construction does is it sort of generalizes that picture of if you have some embedded codimension 1 subspace, you can cut along it and apply Van Kampen. And if that Van Kampen, if the surface along which you're cutting is pi1 injective, then Van Kampen's theorem gives you a graph of groups decomposition, and you get an action on a tree, and so on. And Sageev's construction is a generalization of that to the case where you don't have an embedded codimension 1 thing. Instead of a tree, he's going to find a complex built out of cubes. So instead of just edges, he's built out of cubes. So let me tell you a little bit about how that works. So the setup, you should stop me if I'm telling you things that everyone knows, or if something's not clear. But otherwise, I'm just going to keep talking. So the setup is we have a group G acting on a space X, and we're going to have a collection of partitions of X. So W, which is some set of pairs, maybe UI, VI. And I'm going to assume that they don't intersect and they cover the whole space. Okay, so the picture to have in mind, I'll draw maybe a picture. You might think of G acting on the hyperbolic plane. So G is some group, and then the space is some collection of lines. Is determined by some collection of lines. The collection of partitions is determined by some collection of lines in the universal cover. So you should cut along the line and get 2 pieces, and then include the line in one side or the other as you choose, in order that they cover the whole space and intersect trivially. Okay, so that's the setup that you might get. And where would you get this from? Well, if you have an immersed codimension 1 subspace, then you just look at the preimage of that in the universal cover and do exactly what I just said. Take the 2 sides that it gets you in this case, and include one side in your set in order to include the actual surface in one side or the other. Okay, so that's some combinatorial information, and I want to assume that this collection W is preserved by the G action. Okay, so you want to look at all of the covers of this copy of this immersed surface in the universal cover, translated around by the deck group acting on the manifold, on the universal cover of the manifold. Okay, and then from this, Sageev constructs a certain cube complex in the following way. So this is Sageev's language. An ultrafilter on W is the choice of exactly one of each pair ui vi. So for each of the elements of this partition, we're going to choose exactly one of either ui or vi. Okay, so that, okay, so then this is a completeness condition, so that if we choose some uj, so now the picture, so ui and vi is given by either side of this partition, so maybe this is ui and this is vi. Okay, so if I choose a ui, and now there's some other element of my family over here, so that one of the half spaces determined by the other element completely contains ui. Okay, so maybe this is uj and vj. Okay, if vj completely contains ui, then I definitely have to choose vj. Okay, if I chose ui, I have to choose vj. So if some uj, we choose some uj, and sorry, I got the notation right. So uj is here. This is uj vj, and I chose this half according, and this is uk vk. Sorry, I got my notation, my indices wrong. Okay, and uj is contained in, say, vk, respectively uk. Then we choose vk. Okay, so the picture I'm not allowed, so this picture is not allowed, is the one where I choose this region that doesn't meet uj at all. Okay, so I think about it. I have a codimension one thing that cuts in two, and I have two sides to it. I have the uj side and the vj side, and I'm choosing one arrow each for each subspace. So here, if I choose this, I'm not allowed to choose the one that points away. I have to choose the one that points towards it. On the other hand, if I have one of my half spaces looks like this, and the other one looks like this, then I'm allowed to choose any one of the four. So this one's not allowed, this one is allowed. I'm allowed to choose any one of the four possible choices of half spaces for each pair. This is fine. Okay, if they intersect, then either choice is allowed. Okay, so I'm going to choose. So I have this collection of choices for every codimension one thing. I can choose left or right, and I have to make a choice for every single one. And there's a compatibility condition that is exactly, I can't point away entirely. If they intersect, I can choose whatever I like. Okay, so these are going to form the vertices of some complex. Okay, so I'm going to define a complex, and this is going to be, say, C of W. So the vertices are these ultrafilters. Okay? Notice that one thing I could do, because of this condition, is I could take a point in X, and then my choice is always going to be, well, it's contained in exactly one of these, so I choose the one it's contained in. Okay, that's a collection of ultrafilters. There might be others. There likely will be others. But that's one choice that I could make. So eventually I'm going to want to be in the connected component of those sort of geometric ones, the ones that are obviously there. So, and then the edges are ultrafilters that differ on exactly one choice. So for example, this one's not allowed, but here I could make the other choice for the blue thing and stay with the same choice on the white half space, and that would give me an edge. So here's a second ultrafilter, and there's an edge between those because it differs on exactly one choice. It has to be so you mean it has to still satisfy this condition? Yeah, so it has to be an ultrafilter as well. That's right. So here, this one is allowed. I can change exactly one, but now I break the compatibility condition. So there's no edge here because there's no vertex here. So I'm only allowing the things that satisfy my compatibility condition. And then if I happen to have two that both satisfy the compatibility condition and differ on exactly one choice, then I'm going to put an edge between them. Okay? And then I'm going to put higher dimensional cubes in when I can make independent choices. Okay? There are naturally 4 vertices here, and they're joined. So let me redraw this picture once I've erased Ian's theorem. So just with the same 2 choices, I can okay, so I have an edge here because they differ only on the choice of white. I have an edge here, they differ only on the choice of blue. An edge here on the white, and an edge here on the blue. Okay, and I naturally get a square, and the square is associated to, I could change either one of these independently, and all 4 choices give me allowed ultrafilters. Okay, so if I can do that, then they form the one skeleton of a square, and I glue in a square here. If I have 3 collections where I can independently change any one of them for the 8 possibilities, and they're all allowed as ultrafilters, then I have the 2 skeleton of a cube, of a 3 cube, and I glue in the 3 cube as well. So I make this a flag cube complex, if you like. Every time I see the n-1, the n skeleton of an n+1 cube, I glue in that n cube. Okay, so higher dimensional cubes are glued whenever their boundary is there. Okay, boundary is a cube. Okay, so I saw a 4 cycle that looks like a square, and I glue in a square. I see a 2 sphere with 6 squares on it that looks like the 2 skeleton of a 3 cube, and I glue in that 3 cube. Okay, and so an n cube corresponds to n independent choices that I can make, changing only one element of my ultrafilter at a time. I can do those independently and get all 2 to the n different things are allowed as ultrafilters. So let me just give you a quick example where you might see a 3 cube. I'm just going to keep going with curves in the disk. Now, of course, I need a third thing where I can independently make a choice. I've already noted over here that disjointness gives me a problem with it making these independent choices. So make them all pairwise intersect. You can see here 7 vertices corresponding to the 7 different regions that this cuts it up into. If I moved the green one down here, I'd find the 8th vertex of a cube. So if you just look at this compatibility condition, there's no containment between any of the 3 different pairs that I get. So this condition is empty, and I can make all 8 choices independently, and I get indeed a 3 cube coming from this kind of picture. Okay, so this looks like this induces a 3 cube. Okay? So that's the construction, is so long as you have this collection of spaces, this collection of partitions of your space, then you look at all of the ways of making this choice of 1 each in your pairs, satisfying this compatibility condition, and then you look at these vertices and these edges and these higher dimensional cubes. And you get this complex built out of cubes. And the identifications between the cubes are just the obvious ones you're gluing by a linear isometry along a codimension 1 face or a smaller face. Okay. And so that's the cube complex, C of W, and we normally take the connected component of geometric vertices. I've already told you what they are, but I'll write it down. The geometric vertices are the ones that come from a region. So given x in x, our point, we have the associated geometric ultrafilter that's namely so choose the UI or VI that contains x. And then I just erase the compatibility condition, but you can just check that, I mean, containing x ensures that I definitely have this compatibility condition. So those are the obvious ones that are there. In this picture of the disk with 3 curves, there are 7 geometric vertices, and then the 8th one is allowed but not visible on this picture. If you drew this picture, you would see the 8th one, but then you'd lose the middle one here. Okay, so this is some sort of well, in this case, it's some sort of generalization of the dual complex to this intersection pattern of lines. And of course, in higher dimensions, it's sometimes a little more abstract. Okay, if a group acted on x and W is preserved by the G action, then the compatibility condition is going to be preserved when you move things around under the G action, and the edges and cubes and so on are going to be preserved, and G will act on this cube complex associated to W by cubical automorphisms. Okay. All right. So that's a kind of that's a construction that you can make, and what does it do for you? Well, that's a good question. Inside the square there are 2 lines that cut the square in half naturally. They just cut across horizontally and cut across vertically, and the horizontal segment, well, that cuts sort of correspond. I mean, both of the edges that are dual to the horizontal line across the middle correspond to changing the white direction. So it's sort of naturally identified with the white hyperplane, the white line, and the vertical line is naturally associated to blue, the change of blue. So if you look at mid-cubes, which are just the middle of your cube, in this cube complex, they can naturally see some of the information about the W that you originally saw. Okay, so that's a cube complex, and what kind of properties do you get with it? So Sageev proved that this cube complex C of W is contractible, and in fact he proved it's cat 0. I'll tell you what that means in a minute, but really it means non-positively curved. So it's simply connected and non-positively curved, and so you should expect it to be contractible. So let me just tell you what it means for a cube complex to be contractible. Sorry, to be non-positively curved. A cube complex Y is non-positively curved if the link of every vertex is flag. Okay, so in the link of a cell in a cube, there's a natural simplicial structure. Like the corner is naturally a simplex of one dimension lower. That naturally gives you, on the cube complex, the links want to get a simplicial structure. The simplices may not actually be a simplicial complex because the simplices may not be determined by their one skeleton, but they should be simplicial and flag every time you see the n-1 skeleton of a simplex. It's there. That corresponds in low dimensions to if you see the corner of a cube, the corner of a 3 cube. That's there because there's actually a 3 cube there. Otherwise, a little, so here's a triangle in a link of the vertex. That little triangle, sorry, that's much too small. Let me redraw that a little bigger. Okay. Yeah. So here's the triangle in the link of the cell. So if that was an empty triangle, then there'd be these 3 squares glued together along a vertex. It would be a little bit of positive curvature in your space, and we're wanting it to be non-positively curved. So you get rid of that positive curvature by filling that with a 3 cube, and now it can be filled in a more usual way. So that's what it means to be non-positively curved. If you have a non-positively curved cube complex, it's naturally aspherical. And so cat 0 if it is simply connected and non-positively curved. Okay, so it's the universal cover of a cat 0 cube complex is the universal cover of a non-positively curved cube complex. And as Ian said, you can see the 3 cube by applying this Riedermeister move, moving the green thing down. That gets you the 3 cube that was there from the corner. If you draw the 3 dual squares to this picture, you naturally see, did I get that wrong? Yeah, sorry, that's right. You naturally see that corner of a 3 cube, and then the 3 cube is actually there by applying the Riedermeister move. Okay, so it's a nice enough space geometrically, and there's an action on of the group that you started with on this cube complex. Okay, and then there's a large industry of trying to promote that to a better and better action. We know about certain groups can't act on cube complexes in an interesting way at all, and then this might tell you something about your group. From the point of view of this 2-line outline, you want to find lots and lots and lots of these codimension 1 objects so that we have a very nice action on the cube complex. So let me just tell you a little bit about how that works. No, a little bit, so what you get. So from Kahn and Markovitch's surfaces, one obtains, so this is a theorem that's essentially a consequence of how many surfaces they found and this construction that I explained, but it was written down by Bergeron and Wise. Bergeron and Wise. It says if M is closed, hyperbolic, 3-manifold, then M acts properly and co-compactly, properly discontinuously. And co-compactly on a cat0 cube complex. Sorry, what? Sorry, pi 1 of M. Yeah, sorry. Manifolds are groups. Sorry. Yeah. Then the fundamental group acts properly and co-compactly on a cat0 cube complex. Okay, so that's how one enters into this cat0 cube complex world trying to prove this. But it's still, at this point in the talk, not at all obvious what you want to do with this. Because what does having an action on a cat0 cube complex buy for you? And this is where the special cube complexes enter the story. In the work of Wise and his many collaborators, he spent many years clarifying exactly what kinds of properties you might want for a cube complex, cat0 cube complex with a group action, or the quotient cube complex, it's non-positively curved, to be able to carry out step 2 of this construction. We want to know about lifting immersed things to embedded things in finite covers, and certain kinds of cube complexes are very amenable to having that work out for you. And those certain kinds of cube complexes are called special cube complexes. Okay, so I'll quickly tell you what a special cube complex is. So let me first tell you about hyperplanes. So these are collections of mid-cubes glued along faces. So I'll tell you maybe a little more than that, but really I'd just like to draw you the picture. So if I have a cube, then it has certain mid-cubes. An n cube has n mid-cubes. That just means cut it in half. If you think of a cube as being the standard unit interval raised to the power n, you're just going to restrict to one coordinate being 1/2. Okay, so you choose a mid-cube, and then it meets some adjacent faces in some codimension 1 or smaller codimension face, and that mid-cube will extend uniquely to a mid-cube in adjacent faces. So there's and the minimal such extensions that when two cubes agree, then the mid-cubes agree, is called a hyperplane. There's another one coming down here. There's another one coming across here that extends out into this square. And these naturally correspond maybe to the walls W, the collections W of pairs W that you started with. On the other hand, your cube complex, we should be thinking here not of a cat0 cube complex, which is simply connected, but the quotient by the group action, and maybe the square complex looks like this. So now, if you start at this hyperplane, it meets this square in this line, in this point, which extends to this line, and it extends across. You just keep drawing across, and now it meets this 3 cube in this different hyperplane. Okay, and there's a line of intersection down there. So if you just start in one cube and extend mid-cubes to adjacent cubes and extend those across and keep extending, you'll get a hyperplane, but it's naturally an immersed object rather than an embedded object. This is really coming from a square, an interval, and another square immersing in with this line of immersion. Okay, so those are hyperplanes. They're a natural combinatorial structure that's identified with the cube complex. And the cube complex is really here packaging together these codimension 1 things. As I indicated in that picture up there, the mid of this square, the middle of this square, is naturally identified with the white line, my white codimension 1 thing, and the vertical thing was naturally identified with the blue one. Okay, and now I'm looking in the quotient of the cube complex by the group action, and I get these immersed codimension 1 things. Okay, so I've worked very hard. After Kana-Markovic's very hard work, I've worked very hard in this talk, or Sageev has, or whatever, to turn an immersed pi1 injective surface in your 3-manifold into an immersed collection of mid-cubes in a cube complex. So it doesn't feel yet like we've made very much progress. But the work of Wise and his collaborators shows that this is an incredibly useful structure for promoting the right kinds of immersed objects to embedded objects in finite covers. So let me tell you what a special cube complex is. So a non-positively curved cube complex is special if the following, so this is a definition by exclusion, the following 4 pathologies do not arise. Okay, so what would we like to have happen? We'd like this not to happen. We'd like our hyperplanes to be embedded. So a non-embedded hyperplane, and for each one I'll draw a little picture. A non-embedded hyperplane. So that's like this picture here, or more generally, maybe, or more simply, we just have a collection of squares, and then we start following from one square, and it comes back and it's not embedded. Okay. What we'd like to do with these hyperplanes is they're nice codimension 1 things. We'd like to cut along them and apply Van Kampen and maybe induction. Okay. So a one-sided hyperplane. So these are the things that I'm excluding, and if none of these 4 things happen, then it's going to be called special. So here I just want to think about the core of a Mobius band. So anyone taking notes, draw the core of a Mobius band in their notes. In the audience, it's much easier to do that than for me to do it, so you all know what that looks like. Okay, and it's not 2-sided. It locally cuts the space up only into one piece rather than 2. Okay, for the next one, I'll draw the picture first, and then I'll tell you what it's called, because the terminology is maybe non-obvious. Years of playing cricket. So the next picture is like this. So what I would really like is that a regular neighborhood of a hyperplane embeds. Okay, a hyperplane has a little regular neighborhood that's just the cubes that naturally contain it. It feels like it's a product, and I'd like that product to embed. Okay, it's a product because it's 2-sided, And I'd like not only the hyperplane to embed, and not only for it to be two-sided, but then the regular neighborhood that's just a product to be two-sided. And so this is the picture that happens when that doesn't happen. So there's a square here and a collection of squares. And then you can see what the hyperplane does. Okay. And the regular neighborhood of a hyperplane, I want it to embed. Okay. So this kind of pathology, so I don't like this, is called self-osculating hyperplane. Okay. I'm not going to get into today what the reasons for not liking this osculation is. It's sort of more technical. Really, this is geometrically the key idea. I want to have embedded and two-sided things, embedded sort of related to lifting, to making my immersions embedded. Okay. And then 4, I don't want this to happen. I don't want a pair of hyperplanes to both intersect and osculate. So here's one hyperplane along the middle. And certainly I can't say pairs of hyperplanes don't intersect, because cubes have more than one midcube. But if 2 hyperplanes intersect, I would like them not to anywhere else osculate. Okay? So this is called interosculating hyperplanes. Okay. All right, so I think these two are definitely things that it's clear what you would want them for. This is about embedding a regular neighborhood and not just the hyperplane, and then you don't worry about that for now. If you know the theory, then you got into why that it's important, and if you don't, then it's not worth going into it now. Okay, just and if you don't like the terminology, go and complain to Donnie Wise. Okay, so this is a definition really due to Haglund and Wise, but I think the terminology is Wise's fault. But I'm not sure. Maybe not. Okay. And they proved many really impressive theorems about special cube complexes. And then, so a cube complex is virtually special if it has a special cover, a special finite cover. Okay. Okay. So then there's various theorems. So this is the theorem of Haglund and Wise. If, say, I'm just going to say if X is a compact special cube complex, then pi 1 of X embeds in a right-angled Artin group. Okay, you might not know or care what that is, but and so one thing that you can do with right-angled Artin groups, you can embed it in SLNZ for some n. Okay, so in particular, this group that arose purely topologically or combinatorially, if you have these 4 simple conditions on your hyperplanes and on your pairs of hyperplanes, rather the 4 conditions being none of these happen, then you get an embedding in some other nice group that embeds in SLNZ. So this group is linear. In particular, it's residually finite, which you didn't know at all in advance. And that's one of the things that you can do with this theory, is prove that these groups are residually finite. In this context, I mean, it's the fundamental group of a hyperbolic 3-manifold. It already came to you with a discrete faithful representation into PSL2C. So you can actually say much more. And let me state the theorem, and then I'll tell you, if you like, what some of the words in it mean. So here's another theorem due to Haglund and Wise, and that says if X is virtually special, has a finite cover, which is special, compact cube complex, and the fundamental group is Gromov hyperbolic, then every quasi-convex subgroup of pi 1 of x is separable. Okay. I don't know who wants me to tell. So separability is an algebraic condition, and I'll give it to you in a minute. The algebraic condition is one that encodes the subgroup you should think of as the subgroup corresponding to the image of your immersed map, and being separable means you can lift that immersion to an embedding in a finite cover. Okay, so this condition is the algebraic condition you need in order to lift immersed compact things to embedded compact things in finite covers. Okay, so this is an algebraic notion of that that tells you almost exactly you can lift compact immersed things to embedded things in finite covers. There's a little more to it than that, but that's what's going on. So this separability, and I'll define it in just a minute, this separability is intended to carry out this second stage of this plan. You have something immersed and pi 1 injective, and the subgroup corresponding to the immersion, the image of the thing you're immersing, is separable, means you can lift it to an embedding in a finite cover. So this separability is absolutely key to carrying out the second stage of this step. And I should say this theory is applicable in places other than hyperbolic 3 manifolds. But I just thought I'd focus on that for today. Okay, so I'll quickly define separability. So we have a group G and a subgroup H. H in G is separable if, it says for any element of the group that's not in H, there is a finite group Q and a map eta from G to Q, so that the image of G lies outside of the image of H. Okay? You can witness that G is not in H on finite quotients of the group. Okay? So G is residually finite if the trivial group is separable. You can witness that things are non-trivial in finite quotients. This is a generalization of that to certain subgroups. And then, maybe in the interest of time, you'll have to trust me that the subgroup being separable, say the surface subgroup coming from this immersion being separable, is equivalent to being able to be embedded in a finite cover in this context. Okay. So these special cube complexes, I haven't told you what Gromov hyperbolic or quasi-convex means. If anybody really, really wants me to, I'll do that. Maybe, again, you'll trust me, the fundamental group of a hyperbolic 3 manifold is indeed Gromov hyperbolic. It's one of the archetypal examples. And these subgroups that Kahn and Markovich construct are indeed quasi-convex subgroups. And if you like, it's because they're quasi-Fuchsian. So if one could promote the theorem of Bergeron and Wise, that was probably right there before I erased it, to not only acting properly and co-compactly on a cat-0 cube complex, but that the quotient was virtually special, then we would be done. Okay? And that's exactly what Ian does in his proof that I've also erased. Was there? Okay. So let me just tell you two results that give you a way of building groups that are the fundamental groups of virtually special compact cube complexes. Okay, this is just an if you could somehow prove that these things existed, then these things were virtually special and they existed, then you would be in good shape for this kind of problem. Let me tell you two ways that you can do it. So here's a theorem of Wise, and it's build things one piece at a time via graph of groups decompositions. Okay, so suppose G, I'll just state, is an amalgamated free product, groups A and B over an amalgamating group C, where G is Gromov hyperbolic, A and B are virtually special. Okay, so they're groups. So what does it mean for a group to be virtually special? It means it's the fundamental group. Well, it's got a finite index subgroup, which is the fundamental group of a special cube complex. Okay, and 3, C is quasi-convex in G. Okay, so suppose we have that kind of setup. So I've got my group G, and I managed to somehow split it as a graph of groups, and I understood the pieces, and I understood that it was a nice geometric gluing. So then G is virtually special. It's implied by the hypotheses. I haven't told you why that should be true. I can talk to you about that later if you like. C is quasi-convex in G, and so it's quasi-convex in A and B. You realize C via a map between cube complexes into A and B, and there's a convex C co-compact core for that implies virtually special. Okay, so C is virtually special, but it follows from the hypotheses. You don't need to include it. So Wise used this to prove that if you have a Haken 3-manifold, then you can cut it up along a Haken hierarchy as long as your subsurfaces along which you're cutting are geometrically finite, quasi-Fuchsian. And then you get the whole 3-manifolds, the whole hyperbolic 3-manifold has virtually special fundamental group. So if you already knew that you were Haken, he would prove virtually special. Okay, well, the way I've told this story, that's not what you want to do. You're trying to prove virtual Haken, but that implies many other interesting things, like the separability, and like you can embed your thing in SLNZ, and it was enough using Agel's Riefers condition to prove virtual fibering. So he got Haken implied fibered in that using this kind of a theorem and some other things. Okay, so that's one thing that you might do, is be able to break your group up into pieces you understand and assemble them. And note, there's nothing here about cube complexes. I mean, of course, this is about cube complexes, but it's not at all even clear where the cube complex for G comes, let alone where it being virtually special comes from. There is a tree attached, though. Okay, so there's a tree on which G acts. It's not acting properly and co-compactly. Okay, so, and then the final piece of proving this virtual Haken theorem, which is Ian's theorem, is the following. And that's if G is Gromov hyperbolic, and acts properly and co-compactly, on a cat0 cube complex, then G is virtually special. One remark, so there is a cube complex here, that cube complex X. We can think about the quotient complex X mod G. If G has torsion, which your closed hyperbolic 3-manifold group doesn't, but if it did, then the quotient's not quite a cube complex. It's some kind of Orbi complex, but That's not a big deal. So there's one compact non-positively curved cube complex, X mod G. And the question is that one virtually special, or is there some other completely unrelated cube complex? The answer is every group upon which G acts properly and every cube complex upon which G acts properly and co-compactly, the quotient has a finite special cover. It's independent of which cube complex you act on. There might be many, but they're all virtually special if any of them are. So this is the final piece of that puzzle, is that now it's virtually special, and Haglund and Wise tell you that all of the quasi-convex subgroups, in particular these surface subgroups, are separable, and so they can be immersed in a finite cover. Okay, so that's pretty much all I wanted to tell you. At 4 o'clock, I'll tell you a common generalization of this theorem and this theorem to a more general setting. So simultaneous common generalization of this theorem and that theorem. And that's what I'll talk about. But I won't be at all offended if none of you or some of you don't come. Don't worry. So that's all I wanted to say. Thank you very much.